Today's lecture video is going to focus on the topic of carbonyl alpha substitution reactions, meaning we're going to look at the type of chemistry that you can do on a carbon that is next to a carbonyl, and we'll expand a little bit on that and also mention some functional groups other than carbonyl for which this process also works. So first things first, let me just remind you. So if you will recall that when we were doing hydration of an alkyne, the initial product ends up being a molecule that looks like this, which you will recall is an enol. An enol, of course, is always in equilibrium with its keto form, which would be that. And that equilibrium is what we call keto-enol tautomerization, right? This side, the keto form, is always going to be favored in a case like that. So consider then, based on that, the following. Suppose I were to look at a molecule like this, and I'm going to draw the 3 hydrogens here for emphasis. So remember, you've seen this before, that using the carbonyl as a point of reference, the starting point, any carbon next to it would be an alpha carbon. If there were a second carbon, that would be the beta carbon, the gamma, the delta, the epsilon carbon, and so on. We're focused on the one directly next to your carbonyl. That is an alpha carbon. Now, if I were to take a strong base, Sb, just generically a strong base, that strong base could come and grab a proton from that alpha carbon and kick the electrons in to the alpha carbon. That, of course, is going to result in the following, where the carbon now has 2 protons or hydrogens, 2 electrons, and a minus charge. Now, in terms of energy, this makes sense, and it is allowed because the product that we get, which is this, is of course resonance stabilized, because those 2 electrons can move that way, and the 2 pi electrons can move up on your oxygen. And therefore, what you end up getting is going to be this molecule, in which the minus charge and the 6 electrons are now on oxygen. Now, if you compare this particular species with this one, which we've encountered before in Orgo-1, then you see that it actually looks very familiar, right? You have the carbon-to-carbon double bond here, carbon-to-carbon double bond here. The only difference is here you have an OH, and here you have an O with a minus charge. So rather than being an enol, this is what we call an enolate. Now, the key to what we are about to do here is to consider that the enolate therefore has the alpha carbon being quite nucleophilic, because what happens is, here is my enolate. I have an O minus. Now, when this reforms the carbon to oxygen double bond, it means this carbon, the alpha carbon, is now nucleophilic and can take these pi electrons and reach over and attack any electrophile. We'll just generically say E+. And therefore, the product that you will end up getting here is that on the alpha carbon, I have attached that electrophile. And of course, one of the things that we could attach here would be any alkyl group, and that would be what would be called alpha alkylation if we attach an alkyl group. And in fact, this is one of the preferred ways by which you can extend the size of a chain, because we start off with 3 carbons here, and if we were to attach, let's say, a 3 carbon unit here, we suddenly go from starting material 3 carbons to a product that has 6 carbons. We have, of course, increased the length of the chain, and that would be one of the preferred ways of forming carbon-to-carbon bonds. Now, let me just give you a quick reminder that when it comes to the enol that we saw in Orgo-1, this molecule, which of course is in equilibrium with the keto form, you just remember that in terms of which side is the preferred side, well, the keto form is, and at equilibrium you probably have this 99% of your equilibrium mixture is the keto form, and therefore something like 0.01% is in your enol form. Now, clearly, we actually want to have the enolate form be important because that's the one that can act as a nucleophile and end up attacking. Now, we can actually shift the side of equilibrium that is favored in a system like this by, of course, using either an acid catalyst or a base catalyst. In other words, if I have this, what I might want to do before I introduce the base that's going to deprotonate at the alpha position is, of course, I can add an acid. So let's just say generically an acid HA. So what's going to happen in a case like this is the oxygen can reach over and grab the proton, generate your conjugate base like that. So that is therefore going to have this situation where now the oxygen has a plus charge. And of course, what is going to happen is that your A minus that you kick out here can serve as the base that will come and grab the proton like that. You can kick in these electrons, kick those electrons up to your oxygen, and of course, what that is going to end up producing is your enol, right? And the exact same situation is at play in terms of your enol. You can also, of course, do this. So this would be an example where you're doing acid. You can use an acid to make the forward direction be preferred to yield more of the enol as opposed to the keto. The other way of doing this, of course, is using a strong base. So in this case, what you're going to use is a strong base. So let's say something like sodium hydroxide, which is strong. Because that is a strong base, it reaches over, grabs the protons, and of course, you kick in these, you kick those out, and so that is going to generate this situation where I have this O minus, and if you simply throw in your proton source here, say a molecule of water, you will end up getting your enol. You generate back your hydroxide, which can go back and repeat this process. So that's just a reminder of how you can actually shift the equilibrium. So in this case, this would be using a base to shift the equilibrium to start favoring the enol form as opposed to the norm, which is where the keto form is actually going to be preferred. So that's just how we can make the enol be preferred to do this. Now, a quick word about when we say here that you can use a base to deprotonate at the alpha position. So here we're showing an OH, but really we use much more powerful bases when we're doing this type of reaction. So when we're doing this and we're talking about organic bases to use here, we really mean bases that are like N-butyl lithium, which is nothing more than 4 carbons, your lithium, 1, 2, 3, 4. So that's N-butyl lithium. Or, of course, lithium diisopropyl amide. And in fact, just be aware that very often you will see this written as a combination of N-butyl lithium and LDA. But LDA, lithium diisopropyl amide, you've seen before. It is a situation where what you have is you have a nitrogen and you have isopropyl minus here, and the lithium is a counter ion. So lithium diisopropyl amide is what you have for that. It's a very powerful base. Something like sodium hydride is also a very powerful base. And even you will see in some of these reactions, something like sodium ethoxide is also a powerful base. So these are the bases that we tend to use when we are carrying out this type of chemistry. So let's look at specific things that we can attach at that alpha carbon position. So first, let's look at alpha halogenation. So we can actually attach a halogen at that alpha position. So here is your classic case of this occurring. If I have this molecule, which is acetophenone, this alpha position has 3 available protons that can be substituted for. If you take any aldehyde or ketone and you treat this with a halogen, so let's say bromine, and an acid, and the usual acid, although not the only acid, is acetic acid, which, by the way, get used to the fact that it's normally going to be abbreviated as ACOH, that is acetic acid. What's going to happen here is you're going to end up getting the bromine attached at the alpha position. And this specific reaction, which is a published reaction, has a yield of 72%. So alpha halogenation of ketones, by the way, is actually a known reaction to occur in biological systems. As just a quick example, in marine algae, you find that the following molecules are actually made, and they're used for defensive purposes where they've attached a bromine at the alpha position here. You can actually see cases where these marine algae attach two bromines, and there are even cases where you can see them attaching three bromines at the alpha position. So that is an example of what is seen in nature. So the mechanism, of course, is exactly what we just saw a little bit earlier. You have your starting molecule, which is acetone. And so the acetic acid serves to protonate. So your oxygen reaches over, grabs your proton, kicks the electrons over to the oxygen. And so what you will now have is, of course, going to be this situation, plus charge on your oxygen. And so the acetate, same acetate that you produce, reaches over and grabs a proton, kick these electrons in to form the carbon-to-carbon double bond, kick those pi electrons up on your oxygen, and that, of course, is going to produce this then as your product. And, of course, side product is going to be you get back your acetic acid. And then, of course, what's going to happen here is that in this format, you reform your carbon to oxygen double bond. And so the alpha carbon, this one, which is, of course, nucleophilic, will reach over, and it's actually going to grab one of the bromines in your Br2, so that the result of that is going to be that I'm going to have here double bond OH plus charge here, and you've now attached a bromine at that position. You generate, of course, a Br minus when you do that, and the Br minus is what reaches over, grabs the H in order to get rid of the plus charge on that oxygen. And so here you have your final product, which is your alpha brominated ketone, and of course you also generate HBr as a side product. You see that this reaction, in terms of the mechanism, we can just very quickly say that the rate law is rate is equal to the rate constant K times the concentration of the ketone, first order with respect to that, times the concentration of your acid, first order with respect to that, overall a second order reaction that happens here. So a quick little thing here, because we are abstracting a proton, and you know that if you want to prove that abstraction of a proton is the key step here, you do what's called a kinetic isotope effect reaction. So just to illustrate what we mean by that, if I were actually using D3O+, right, an acid where it's deuterium as opposed to regular hydrogen, what you will first get is going to be the deuterium, of course, is what's going to be there. This is your intermediate. And then when you add your proton source, which is another D3O+, this is the fast part of the reaction. Then what you will end up getting is the following. So this is where the deuterium ends up on the alpha position. So this being the slow step, this is the rate determining step for this reaction. Now, when you're doing an alpha halogenation reaction, what if your starting material is not is like this one, where it's not symmetrical? Because now that's an alpha position and that is an alpha position, but they're not the same as in the case of acetone that we just looked at. If I were to do this reaction, so again, let's use bromine and acetic acid. So we're attaching a bromine. The question is, do you get the bromine adding at the alpha position on the right, which is the more substituted position, more sterically hindered, or the alpha position on the left, which is the less substituted one? Well, you find that in these reactions, your product actually ends up on that alpha position. So the halogenation will end up on the more substituted carbon, and that is the common pattern that you see. So the halogen is added to your more substituted alpha position, which is the one on the right. Now, remember when we were looking at addition of nucleophiles to alpha beta unsaturated ketones and aldehydes and so on? Well, here, just as a quick little side thing here, that you can actually generate an alpha beta unsaturated carbonyl, in this case a ketone, by doing nothing more than adding a base here. So for example, if I were to add pyridine, which you all know is a base, warm this up, what's going to happen is I'm going to get dehydrohalogenation to yield an alkene, and the alkene that you're going to get is that one following Zaitsev's rule, which of course is an alpha beta unsaturated ketone that we're making here. So that's one of the preferred ways of making alpha beta unsaturated ketones. Okay, so why do you prefer this? Well, just for a second, when you deprotonate, so you saw the mechanism that you're going to deprotonate at those two positions. So let us consider the two possibilities here. If I were to deprotonate at this alpha position, then this is going to yield the following enolate, which is going to be this one, where the double bond is here and I have O minus. If, on the other hand, I were to deprotonate this position, that alpha position, this will form the resonance structure like this, and so this will end up giving me this enolate. So this one is less substituted, this one is more substituted. In other words, it's Zaitsev's rule that we're looking at. This one is more substituted, and therefore it is more stable by Zaitsev's rule. So this is going to be preferred, and that's the reason why you end up getting the alpha halogenation on the more substituted position in that example. All right. This reaction, by the way, you could also do it using chlorine and acetic acid, and you would be attaching a chlorine at that alpha position. So that works for aldehydes and for ketones. What about alpha halogenation of a carboxylic acid? Well, this actually, so of carboxylic acid, this one actually has a name to it. This reaction is called the Hell-Volhard-Zelinsky reaction. And this reaction is used to attach strictly bromine at the alpha position in a carboxylic acid, not chlorine or any other halogen. And you know, if that works, then why change a good thing? So the way this is going to work, as a quick example, is let's say that I have this 4-carbon carboxylic acid, which of course is butanoic acid. The conditions that I'm going to use are step number 1 will require bromine and phosphorus tribromide, and step number 2 requires hydrolysis, which is water. And what I'll end up getting as the product is that at the alpha position, which is here, I am going to attach bromine. So that is the Hell-Volhard-Zelinsky reaction. Okay, so how does this reaction actually occur? What is the mechanism for it? So what happens here is that if I have a carboxylic acid and I treat this with phosphorus tribromide, We saw this when we were doing nucleophilic acyl substitution type reactions that will end up generating the acid bromide. So that is the first step. So what happens is that under the conditions in which this is occurring, you are going to get a shift, a rearrangement. And so what I'm going to get here is going to be this, where we'll have Br and OH. So this simply means here I have two hydrogens. One of these hydrogens migrates there. Pi electrons will grab this, and then the two electrons here kick in here to form the carbon-to-carbon double bond. So I end up getting that, which is an acid bromide. This is generally called an acid bromide enol. And then the bromine is going to come in, and I'm going to attach the bromine at the alpha position. So what I'm going to end up getting from this is going to be here, bromine is going to attach at that alpha position. Problem is, this is not an acid, this is still an acid bromide, and we know from when we're doing the chapter on nucleophilic acyl substitutions that you can take any acid derivative, and an acid halide is a derivative, and you do a hydrolysis, which is where step number 2 with the water comes in. And what you end up doing is converting the acid derivative, which is your acid halide, back to the acid. The bromine is already attached there, and that is your final product that you have. Now, this alpha halogenation is normally done, notice, under acidic conditions. So we saw the alpha bromination or chlorination using bromine or chlorine and acetic acid, and we just saw the Helmholtz-Zielinski reaction that's occurring on carboxylic acids. But you can actually do alpha halogenation in basic conditions, and this situation is called the haloform reaction. Haloform reaction. So here's what I mean by this. If I were to have the following ketone, I can treat this with sodium hydroxide. That's why this is under basic conditions, and bromine. And what I will end up making from this is that at the 1 alpha position that can be substituted for, I'm going to add a bromine. Now, one of the things you will find very quickly is that this is actually more reactive than the original one, and so it generally undergoes a second bromination. So because this is more reactive, and by that we mean compared to the original one where you did the alpha halogenation, it means that you get a second step, you can get a second reaction occurring. And so what you're going to get in that case is adding 2 bromines, since I have 2 available hydrogens at the alpha position in the starting material. So here what happens, of course, is that the base is going to deprotonate the alpha position that has protons available for deprotonation. So it means I'm going to deprotonate here. That is what the sodium hydroxide, which is a strong base, will do. And that, of course, is going to attack the bromine. So that reaches over, attacks the bromine, and kicks that out, and you get that product. And you can repeat that reaction, and you are going to get a second reaction occurring, and you get this final product. Now, this same reaction that you see, what if I were to use methyl ketone? So in other words, as long as on one side I have a methyl group here. So just to bias this, we have 2 alpha positions, this alpha position, but clearly this alpha position has no protons to take away, so nothing happens there. This is the alpha position where the reaction is going to occur. So if I take this and I use excess base and excess of the halogen, so step number 1, I use sodium hydroxide, and I'll just specify excess, and bromine, and I'll just specify excess. And then, of course, since I'm doing the reaction in basic conditions, before I do my extraction, etc., I want to add an acid to neutralize any unreacted base that I have. It turns out that what you are going to get as your product here is going to be a carboxylic acid, plus the side product is going to be carbon with 3 bromines and a minus charge here. This is really the haloform reaction because you're producing bromoform as your product. Technically speaking, this is really the haloform reaction. So what happens here is, of course, you're going to add 1 bromine, then 2, then 3. So what you're going to get from that is going to be this situation where I have Br, Br, and Br, because remember, after the first alpha bromination, that becomes more reactive, and you can add a second, which is more reactive, and you can add a third. And so at this point, this is where your sodium hydroxide comes in. What your sodium hydroxide is going to do is it's going to come in, act nucleophilically, attack here. You're going to kick these electrons up on your oxygen. And so that is going to generate O minus, OH here, and you have that carbon with 3 bromines. So this will reform your carbonyl to give you the acid, and these electrons are going to be kicked in here. So you end up getting carboxylic acid here, carbon with 3 bromines and a minus charge on it. So that this reaction, by the way, also works with chlorine and with iodine. Fluorine you stay away from. So the haloform reaction in its full glory. All right, so that's how you would attach halogens to the alpha positions of aldehydes, ketones, and carboxylic acid. Now, I said earlier that alpha alkylation is one of the main ways by which you extend the length of chains. So in alpha alkylation, remember, what we're actually doing would be, for example, if I have cyclohexanone, I treat this with a strong base, such as lithium diisopropylamide, LDA, and then I'm going to add an alkyl halide. And what I will end up doing is attaching the alkyl of the alkyl halide at the alpha position, so I extend the size of the chain. Now, the LDA is going to first deprotonate, and so I'm going to get this. And then this, of course, is what's going to attack my alkyl halide. You attack this, kick this out, and you're going to get that. And of course, side product will be X minus. Now, one thing to keep in mind is that this is an SN2 reaction. So all of the restrictions that normally apply to SN2 will apply here. Namely, this reaction won't happen if the alkyl halide is tertiary. It will happen if it's secondary, but not as well as if this is primary or methyl, right? That is stuff that you already know from your Orgo 1. Now, what if your starting material is not symmetrical? By this I mean, what if what I have is this as a starting material? I have an alpha, which I'll call alpha 1 on the left, and an alpha, which I'll call alpha 2 on the right. The alpha 1 is less substituted. The alpha 2 is more substituted. Now, we just went over the fact that if I'm doing an alpha halogenation, you will normally, in a situation like this, add the halogen at the more substituted alpha position, which would be at alpha 2. But of course, what happens here is I can think of this happening 2 ways. I can add a base which deprotonates at the alpha 2 position, so that what I end up getting then is going to be this enolate, so that when the attack on the Rx occurs like that, then the product that I'm going to get from that is going to be where the R has added at that position. The alternative to this, of course, is what if I actually deprotonate the alpha 1 position to give me that enolate, so that when this reforms and this attacks, it's going to attack the Rx there, you kick that out, so that the product that you will end up getting from this one, I'll put it over here so we can see it clearly, is going to be where the R has added at the alpha 1 position. So can we control which of those we actually get? The answer is yes. because if you focus on this enolate, this one is a tetra-substituted enolate if we consider an O as a substituent. This enolate is a tri-substituted if we consider the O minus to be a substituent. So therefore, based on Zaitsev's rule and our understanding of which one is more stable, Zaitsev's rule says this is more stable. So therefore, this is what we normally call the thermodynamic enolate, and this one is the one that we call the kinetic enolate. So notice that the kinetic enolate leads to the substitution at the less substituted alpha position on the initial product, alpha 1, but the thermodynamic product leads to the R adding to the more substituted alpha position, or alpha 2, in that. So how do we actually control this? You do it by the choice of base and your reaction conditions. So if the problem is, or the situation is, because this is more substituted, it is less sterically accessible. Because this is less substituted, it is more sterically accessible. So if I were to use a small base has no problem reaching the alpha 2, and therefore I would use something like sodium hydride, which is very small, and use room temperature. However, if I use a bulky base, it cannot access the more sterically hindered alpha 2 position, and so that results when I use something like lithium diisopropyl amide, which of course is a bulkier, more sterically hindered base itself, and usually we're going to use low temperatures in the order of minus 78 degrees. That leads to the kinetic enolate, and therefore you see the two different products that we could actually get. So the final product is going to be based on the conditions of base and temperature that we use. So a couple of quick little examples of that to illustrate what I mean. So let's say that I have this situation. I treat this with LDA minus 78 degrees Celsius, and then I'm going to add methyl iodide. Well, I have alpha 1 here, and I'll just put alpha 1 and alpha 2 here. This is a bulky base. If it is a bulky base, it cannot access alpha 1. It's too sterically hindered, so it will deprotonate at alpha 2. So that is where I'm going to add the methyl group. So the product that I'm actually going to end up getting here is methyl group adding at this alpha position, which is the alpha 2. Again, the reason is that that's the position that's going to be deprotonated with a bulky base. If I have an example like this one, so in this case, alpha 1 is more sterically hindered, more substituted. Alpha 2 is less sterically hindered. If I were to take this one now, and I'm told I treat this with sodium hydride as the base, and I'm adding benzyl bromide, which is a primary alkyl halide. Because this is a small base, it can access alpha 1 deprotonate here. So that's the position where I'm going to add the alkyl group. So for that, the product is therefore going to be, here is where I add the R of the Rx. That's the case. So here's a third example to drive home this point. So this is symmetrical. So this is symmetrical. So here are the conditions that they give us in this case. First, you treat with LDA. Second, you add ethyl iodide. Third, you treat with LDA again. And four, you add methyl iodide. So what's the product that you're going to get? So let's do this in sequence. Because this is symmetrical, when the LDA is added, step number 1, really, it doesn't make a difference where I deprotonate, so I'll just say here on the right. Step number 2, when I throw in my ethyl iodide, that carbon will attack here and kick that out. So therefore, what you will end up doing is attaching the ethyl at that position. But now there is, of course, a choice to be made between that substituted alpha position and more substituted, less substituted. So if I'm going to, in step number 3, this is step number 2, in step number 3 add LDA, because that is a bulky base, that means that I'm actually going to prefer to deprotonate at that position. And so then in the fourth step, when I add methyl iodide, that is the nucleophilic carbon which adds here, and you kick that out. So my product is going to be where I add the methyl group there. So that is the product that I'm going to get, an alkyl, an ethyl group here and a methyl group there. So that's just to illustrate the whole business of kinetic versus thermodynamic enolate. Okay, here is a question. If we're saying that the alpha position of something like this can be deprotonated, right, with a base, so let's say something like LDA, we're deprotonating at that position to give us this, and we of course know that's going to form the enolate, so that's going to be this. So what we're really saying is the alpha position is actually quite acidic. There's a low pKa, and so a good, nice, strong base is going to deprotonate at that alpha position. So now let us consider the following molecule. What if what I have is this situation? So notice there's an alpha position here and an alpha position here. This is symmetrical, so this alpha position is the same as that. Alpha 1, alpha 2. They're not the same thing, because what happens here is if I deprotonate at the alpha 1 position, then what I will have is this situation, and this can form a resonance structure with the carbonyl on the left, and therefore what I'm going to have is this resonance form. If I deprotonate, however, at the alpha 2 position, the one in between the two of them, notice that in that case I can actually form two different resonance structures. I can form a resonance structure with the carbonyl on the right, which means I will end up having that enolate. And of course, I can form a resonance with the carbonyl on the left, which means that in that case, this is the enolate that I will end up forming. So here I have two resonance forms that I can get if I substitute the alpha 2 position in between the two carbonyls versus only one resonance structure. That tells you that this is the preferred position. So the alpha 2 is more acidic by far compared to the alpha 1. So we can take advantage of that situation in order to carry out interesting chemistry. Well, I'll get to something else in a bit. So here, then, we're saying that in any system where you have an alpha carbon in between two carbonyls, that is going to be by far, the more acidic position, alpha position, and therefore the position that's going to be deprotonated. So that allows us to do chemistry such as the following, which is called the malonic ester synthesis type reaction. So this is what malonic ester happens to be. So in malonic ester, it's a diester. I have this situation. So this is normally just written for short. Instead of writing it out in its full glory, we just say OET for the ethoxy ester, the ethoxy or the ethyl ester. All right. If I take this molecule and treat this with a base like sodium ethoxide, ethanol is the solvent, this alpha position in between the two is going to be deprotonated. So what is it that I'm actually going to get in this situation? Well, I'm going to get that, because keep in mind there are two protons here, so you can take off one proton there. So let's specify that it's one equivalent of the sodium ethoxide that I'm using. If I have this now, and I were to treat this, let's say, with ethyl iodide, the nucleophile attacks electrophile, you kick that out, nice SN2 reaction, and that means that the product that I'm actually going to get from that reaction is going to be this one where I've attached an ethyl group. Now keep in mind, there is still a proton there that in theory can be removed, and indeed, if I treat this with another equivalent of sodium ethoxide in ethanol, I will deprotonate that position. So the product that I end up getting there is going to be this one, where I now have a new nucleophilic position there. So let us say that I now treat this with a nice primary alkyl halide like that. You attack here, you kick that out, nice SN2 reaction. And so therefore, what I am going to have here is this situation where I had added an ethyl, and now I add this isobutyl, right? Now, if I don't do anything else here, this is my final product. But it turns out that if I actually hydrolyze this by adding an acid and usually warming this up, what will happen is one of these ethyl groups is going to, in essence, go away, and I say go away in quotes, and instead an H will be placed there, and the other ester is going to be converted to an acid. So I'll just put a little dot there to keep track of that. So here's the product. Here's the little dot that I'm keeping track of. It has an ethyl group, which is that. It has an isobutyl group, which is that. So this ester group on the left goes away, and instead you'll get a hydrogen. This ester group on the right becomes an acid. So there is my final product. Now notice if I were to rewrite this in its more normal form, 1, 2, 3, 4, 5. What I actually have is pentanoic acid. So 1, 2, 3, 4, 5 here. This is 1, 2, 3, 4, and 5. At position 2, I have an ethyl group, which is there. And at position 4, I have a methyl group, which is there. So there's the product that I've actually made. Now, you might look at that product and wonder, wow, how did I get to here from here? Well, because of this final hydrolysis. So what happens here is that this hydrolysis is followed by a decarboxylation step. So I'm going to show you the decarboxylation step by itself. So what I have is, again, to keep tabs, here's my little dot that has an ethyl group, an isobutyl group, and it has an ester and another ester. Now, we already know from when we were doing the chapter or the section on derivatives of carboxylic acid that if I actually treat this with an acid, I'm going to hydrolyze any acid derivative back to the acid. So that means that what I'm going to get here is that this ester becomes an acid. So I'll redraw it just here to emphasize the point. So I have that, that. And so what that means is I have the ester on the left, which is hydrolyzed to an acid, which is that one. And the one on the right is hydrolyzed to acid also. I do it this way because you can see the decarboxylation step. Under the heat that's happening here, the hydrolyzed product is going to do the following. So the oxygen takes the pi electrons and grabs that proton. These electrons are therefore kicked in here, and these electrons are therefore kicked into that carbon. If you really follow what is actually happening, my mistake here, and this is kicked into that to form a double bond at that position. So therefore, here's the little one we're using to keep track of things. So there's that carbon. It has an ethyl group. It has an isopropyl group. Okay, there's no longer a carbon-to-carbon bond here, but instead there's a double bond here, which is like that. And that carbon has an OH, which is like that. And it has another OH here when this oxygen picks that up. So I have that. And I have formed CO2. So I've given off carbon dioxide gas, which makes this reaction energetically very, very favorable. What I have here is, of course, an enol. And all enols, this just happens to be a double enol, will automatically undergo, we learned this, keto-enol tautomerization to yield the keto form. So here is the keto form. Again, starting from here, so we keep tabs. We have that. And what that means then is that here I'm going to have the enol become the keto, and there is my carboxylic acid. So again, just to summarize, the initial ester, when treated with the acid, will have the two ester parts reduced to acids. You get the decarboxylation occurring, and you will end up getting that as your final product. So it's a very interesting reaction because it makes very, very, very valuable products. So for example, let's just start off and do a quick example. Let's say that we have malonic ester, which is like that. I treat this with 1 equivalent of sodium ethoxide, and let's just say that I add that nice primary alkyl halide. Then what I'm going to get as product is going to be that at this alpha position here, I have deprotonated once, and I have attached this R of the alkyl halide, and so therefore I have attached this group. There's still a hydrogen. So if I add another mole of sodium ethoxide, and this time let's say that I use 1 bromobutane. That means I'm going to add a butyl group here, and so the product that I end up getting from that is therefore going to be this, where I had originally already attached this, and now I'm attaching a 1, 2, 3, 4 carbon unit, 1, 2, 3, 4. And if I don't do anything else, that's the end of the reaction. But if I add the acid, that's going to convert the two esters to carboxylic acids. And then I heat. The heat is going to, of course, make this decarboxylate. So again, to keep tabs, I will highlight the original carbon, which is your alpha carbon that I have here, which is this carbon, which of course is that carbon. So when this is done, what that carbon has is, I had added this to it in the first step. I had added this to it in the second step. One of those esters goes away. The other ester therefore becomes a carboxylic acid, and there is my final product, right? If you just follow, you will see it's fairly simple to figure out what is happening. Now, here is a version of this reaction. So if I have my malonic ester, and what I do here is I treat this with sodium ethoxide, so I'm going to deprotonate, and then I treat this with the following 1,4-dibromobutane. So here's the reaction that we know occurs. You kick that out, and so therefore the product that I'm going to get from that is going to be the following, where I have added this molecule, right? To keep tabs, 1, 2, 3, and 4. So that's 1, 2, 3, and 4. There is, however, still a proton here. So if I were to take this and treat with sodium ethoxide, again, what I'm going to do is deprotonate. So I'll just write it out here for emphasis. Right, 1, 2, 3, 4. I've deprotonated. Now the difference here, when I start off with that dihaloalkane as opposed to just a monohaloalkane, is that this has already an alkyl halide here to be attacked. So this carbon reaches over and attacks carbon number 4, and you kick that out. So you are actually forming a ring. What's the size of that ring? 1, 2, 3, 4, 5. So again, here's the original alpha carbon that I started off with. Here is where I added the R group the first time. That's the carbon that is deprotonated and attacks. So 1, 2, 3, 4, 5. So what I end up having here is a 5-membered ring. So here's the carbon that did the attack. What does it have? Well, it still has the 2 esters. So an ester here and an ester there. And again, if I don't do anything else, that's the end of the reaction. But if I were to do my acid hydrolysis and warm, I'm going to do decarboxylation. So that means that what happens is one of the esters goes away and is replaced by a hydrogen, and the other one becomes an acid. So that is how we can make cyclopentane carboxylic acid. If I had wanted to make the ring 6 carbons, instead of using a 4-carbon dihalo at the beginning, I would use a 5-carbon dihalo. And if I wanted to make a 7-membered ring at the end, I would use 6 carbons in the dihalogen that I use for that. So that's malonic ester synthesis. Now, what if you have something that is closely associated but not quite the same? This is what is called acetoacetic ester synthesis. Slight change here, and here is the slight change. All right, so in the malonic ester, we had ester on the right, ester on the left, but here, instead of an ester here, I just put a methyl group, so that is a ketone and an ester. Same situation. If I were to treat this with one equivalent of sodium ethoxide, and then I were to use that alkyl halide, then what's going to happen, we know by now, is the alpha position here in between the 2 carbonyls is, of course, going to be alkylated. So I add the isopropyl group. If I take this molecule and I were to add to it again another equivalent of sodium ethoxide, and let's just say a butyl 1-bromobutane there, then what I have is the second alkylation. So I had already added the isobutyl. So now I add the butyl. So here's my alpha carbon. Here is my alpha carbon, 1 alkylation. Here's my alpha carbon, 2 alkylations. If I don't do anything else, it's done. What if I do the hydrolysis and heating? So what's the difference? The difference here is I don't have 2 esters. I only have 1 ester. So in that case, what happens? Well, what happens is the ester goes away. I get a decarboxylation just as in the malonic ester, but what it means is that that ester is going to be replaced by a hydrogen. So I don't have to show the hydrogen. It's a line structure that we're using, and here is my final product. Right? Very similar to the malonic ester synthesis. Now, you have to always be aware when they throw in something that might look different, but it's really the same thing. This is what I mean. Suppose you have the following molecule, and you are told you treat this with 1 equivalent of sodium ethoxide, and then let's say that I use benzyl bromide as the alkyl halide. So here is the alpha position in between the 2 carbonyls that's going to be deprotonated, and of course it means I'm going to add that. So once you deprotonate here, that is going to attack here and you kick that out. So the product that you're going to end up getting is going to be this, where I've added my benzyl group. Now the difference between the acetoacetic ester versus this one is that at the alpha position here I have 2 protons to deprotonate, but at the alpha position here there's only 1, and I've already done it. You can't do a second alkylation because there isn't a second proton to take away at that alpha position. And so if you don't do anything, that is your final product. Now if what you do is, of course, add your acid and heat, this ester again is going to go away. And so the final product that you will end up getting is that at this position I have added the benzyl group. Now the key to this is, notice very carefully. Here is acetoacetic ester, and here is the other starting material that we just started off with. This is what I mean by you just have to understand the process and recognize that it's the same thing. Because if I just go ahead and cover this briefly, if I were to cover that part of the molecule like that, you realize that what we have is exactly the same thing. I get the one on the right by doing nothing more than tying this up in the form of a ring, and that's what I have. So it's the same chemistry that's going to happen. The difference, of course, is that before I tie that up in the form of a ring, I actually have 2 protons and I can do a double alkylation. But here, there's only 1 proton, and therefore it is single alkylation, right? So just be aware that that's exactly the same thing. So that is acetoacetic ester. Now, a quick couple of things to note before I end. Now, if I have, let's say, this situation, there's an alpha 1 here and an alpha 2 here. We know the alpha 2, which is in between the 2 carbonyls, is of course far more acidic, so normally you're going to deprotonate there. Now, what if, however, what I wanted to do is to alkylate at the alpha 1 position? What if this is where I wanted to add an alpha group? Then how do I do that if the alpha 2 is the more acidic position and that's the one that is preferentially deprotonated? A very, 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 very simple thing is what we do. What I would do is use 2 equivalents of sodium ethoxide. You will notice by now that I've always been putting 1 equivalent. And by doing that, you first deprotonate the alpha 2, but the second equivalent deprotonates here, and that is where your position is going to be deprotonated. So if I were to treat this with 2 equivalents of sodium ethoxide, and then let's say throw in isobutyl chloride, the product that I'm actually going to get is the one where I have added the isobutyl group at the alpha 1 position. So that is the product that I'm going to get. Now, if I had treated that starting material with just 1 equivalent, then it would just be deprotonation as normal at the alpha 2 position. So you need to be aware of that situation. All right. Final thing I want to say is this reaction isn't limited only to aldehydes and ketones. So let's just say here, other functional groups, what happens? Just run through a quick series of things. Let's say that I just have an ester here. Well, that's an alpha position that has acidic protons. If I were to treat this, let's say with LDA, solvent that's used here is THF, tetrahydrofuran, and I then use isobutyl bromide, then of course what's going to happen is I'm going to add the isobutyl bromide at the alpha position. I can have an ester in cyclic form like that. These are called lactams. If I were to take here and do the exact same reaction, treat with the same base, same thing, that's an alpha position that is acidic. And so therefore, the product that I would end up getting there is that you alkylate at the alpha position, so you attach your isobutyl group. Now, I could also have, for example, a nitrile. So nitrile is just like your carbonyl. That is the alpha position. Because if I were to treat this with a base and get here, this can form a resonance structure with that carbon this way. And so what you have is here this type of situation with a minus charge there. And so that alpha position is also highly acidic. So if I were to take this molecule and I were to treat again, let's say with LDA, and let's just say iodoethane, then the product that I'm going to get is that the alpha position is going to have the ethyl group added to it. Another thing would be, for example, what if I have a nitro? Well, that's the alpha carbon relative to the nitro. If I were to take this and treat this with, let's say, sodium ethoxide, and then let's just say ethyl iodide, then that means the alpha position is where you will add this, which is your R in your alkyl halide. And just like we had the malonic ester and acetoacetic ester situation, there is nothing, of course, preventing us from having this situation where the alpha carbon here, which has 2 protons, is highly acidic because it can form if you deprotonate, you can form 2 resonance structures. So for example, if I were to treat this with sodium ethoxide, and then I add, let's say, iodoethane. So what I'm going to get then is an initial protonation where I add to my alpha carbon, I add the ethyl group, which is that. And if I take that and I treat again with another equivalent of base, sodium ethoxide, and this time, let's say I use the isobutyl iodide, then what it means is I'm going to get a second alkylation at that alpha position where I add isobutyl group. Now, this is technically speaking an acid derivative. So if I hydrolyze this with an acid, I would convert these to 2 acids. And if I then heat, I could theoretically decarboxylate and do that reaction. And of course, the alpha carbon can be in between 2 different things. So if I were to have, let's say here, this alpha position is in between an ester and a nitrile, same situation would actually happen. Let's say that I treated this first of all with 1 equivalent of sodium ethoxide, and I were to add ethyl iodide, and then I do another deprotonation with sodium ethoxide and add my isobutyl iodide. So what am I going to get from all of that? Well, the product is going to be the following. So in this case, I'm adding, here's the alpha position. First, I added the ethyl group here. Second, I add my isobutyl group here, and that's what I have. So to go back then, if I were to add an acid and actually heat, then this ester will be converted to the acid, this nitrile to the acid. So I'll write it out so that we are reminded of that. There's the alpha carbon originally, 2 groups that were added. And so that ester is converted to an acid. And of course, the high temperatures will end up doing the decarboxylation. So what you will end up getting in this particular case is that, right? So that's just to show you the reaction is versatile and can be applied to a variety of functional groups. And that is the end of this particular lecture video.